But scientific method, Chem 1A begins with the scientific method, you know, in Petrucci. Did you guys have Petrucci for Chem 1A? You know, the textbook, did anyone not take Chem 1A here? Everyone took Chem 1A here? All right, then this is the book, basically. It's just the second half of the book. Do you guys have the e-text, or what are you guys using? The e-book? Yeah. They only have like 4 copies, I think, and it's really expensive. It's over $300, right? The ebook for the lifetime license is like $85, I think. You probably already have it. Or the I think it's 6-month license, it's 50. You know, if you're going to get one, you might as well get the lifetime. You know, the book can be useful for other classes as well. But one of the things from Chem 1A is the scientific method. Now, I have it listed a little bit differently than they have it in Chem 1A. You know, there's no right or wrong, you know, but in general, this is how I did science, and this is how everybody I knew did science. And when I look at it, you know, there's some variation, but one of the common things, one of the things that I see a lot when people are asked about the scientific method is to develop a hypothesis first. You know, developing a hypothesis first is, for me, very difficult, you know, extremely difficult to do. You know, did somebody hypothesize the periodic table before generating it? You know, I hypothesize it's going to have this shape. And then I hypothesize that we can put these elements in here like this. Do you think somebody hypothesized that? And then I'm going to go out and test it. You know, I'm going to hypothesize this periodic table exists. It's going to look like this. I'm going to go test it. That's, to me, is just way too difficult. You know, instead, and I saw some people had this. Instead, for me, science starts off with observations. And then some people said, well, from those observations, we go to a hypothesis. We don't necessarily go to a hypothesis from those observations. Like, for example, here, let me give you an observation. You know, none of the scientists observe things, they count on data, right? We collect lots and lots of data. It's always good. And so let's say we collected some data, and this is the data I have here. So this is the data, what's your hypothesis? Or this is the data over here. Okay, here's the data, here's your observation, what's the hypothesis? How are you going to hypothesize from that data? You know, normally when people look at a chart like this, I got the chart, you know, they just stop here. This is observation. And so they have this chart here, and then, oh, okay, I can use the chart and just look it up in the book or look it up online. And we use the chart, but that's not where we stop. We don't just stop at observation. And then to come up with a hypothesis for this, well, requires a bit more work. And so even after the observation, I don't think a hypothesis is necessarily appropriate at this stage, you know? What I think, after the observation, what we do is we look for patterns and trends. This reminds me of of an example of this that I heard from a TED Talk. This TED Talk was from a social scientist. And what she did was she took a lot of data from people and wrote it down. But, you know, okay, that's the observation part of the scientific method. The next step was what caught my attention in this TED Talk. And what she said she did was she took all this data, you know, each page was a person and their information, and then threw it all over her floor, grabbed a chair, sat down, and just stared at the data, you know, for a long period of time. You stare at the data. And I thought, wow, that's exactly what I do. You know, you get a data table like this, and what do you do? Well, you just stare at it, and then you look. Are there any patterns? Are there any trends in that? You know? And after let's say, a long period of staring, you might see some patterns come up. Yeah, like one of the patterns here. I see a pattern, HI-HBr-HCl. Do you see that pattern? HI-HBr-HCl. Now, this is based on acid strength. Acid strength just comes from observations. You know, when we take observations, this acid is stronger than that other acid, right? So we look at this, and then we think about that pattern, and then, okay, there's a pattern there. And then we might think about, hypothesizing. Here, now this is probably an appropriate point to think, why is that pattern like that? Why isn't it like HCl at the top, HBr, HI? Because chlorine, when I look at the periodic table, I see it goes chlorine, bromine, iodine. And it's inverted over there because it's iodine, bromine, chlorine. You see that? So these are the types of things that might come up. Sometimes these patterns are very strong, Sometimes these patterns we can generate into laws. For that particular pattern, I wouldn't say that's a law of acids, or this is the law of acids. The law of acids tells me, it tells me the acid strength in certain directions. But for other things, we see this. Let me give you some other examples of patterns. So, for example, did you hear the story about the apple falling from the tree? Isaac Newton? You heard that? So let me tell you, did Isaac Newton hypothesize that gravity existed and then went out to test that hypothesis by dropping apples from the tree? What came first? Apples dropping from the tree, or his hypothesis about gravity and gravitational pull of the center of the earth and this kind of stuff? What do you think came first? The apple falling from the tree. So Newton observed apples falling from the tree, and then this came out to be a consistent, reproducible pattern. And then he comes up with the laws of motion. And it wasn't until much later then, the hypothesis and the theory of gravity, became a reality. And so when I think about, science, if you start off with a hypothesis, that just seemed very difficult, And most of the scientists that I was working with got jumbles of data like this. You get jumbles of data like this, and then you stare at it and see, is there a pattern? So when we look for patterns, we might take that jumbles of data and try to graph it, or see if there's a trend, trend line in Excel or something like that, or curve, or see if there's some kind of mathematical pattern. If there's a mathematical pattern to that, then we can get a law, like for example, Charles. Did Charles hypothesize his law, Charles' law, first, or did he take observations first? Charles was, volume and temperature. So did he do his experiment first, or did he hypothesize that, I figured that the gas volume was going to be linearly proportional to temperature, or did he just collect the data and then graph it and see? No, he collected the data. And so when we think about other examples, Charles, what did Charles do? Charles did the scientific method. He took observations. What happened to the volume as he changed the temperature of the gas? He noticed the pattern of trends, he graphed it, and then he came up with a law. The law is very simple, mathematical. These are what we call empirical laws or empirical equations. Empirical laws or empirical equations are just the most concise way of defining a pattern. If you can define a pattern mathematically by a simple mathematical equation, then that is the fewest number of words, or the fewest number of symbols or characters, whatever, that you can have to define such pattern. Okay, let's see. When we go this way to a law, these are called empirical. Empirical law or equation. So let me give you an example. The ideal gas law, PV equals nRT. Did somebody hypothesize that? No. The ideal gas law, PV equals nRT, was derived from observations. And so what we did was, there are a whole bunch of patterns and trends. You had Charles' law, Boyle's law, Gay-Lussac's law. All those laws were combined into the ideal gas law. Now, the ideal gas law, well, there are different ways you can describe it. You can just say, oh, when the temperature increases, the volume expands. If the number of moles of gas increases, the volume expands. The pressure, if the volume can't expand, then the pressure increases. This type of things. There are different ways of describing it. But the most concise way of describing how gas behaves is via the empirical equation. So you can take all those words, like, okay, this is what the gas is going to do when you change these, and condense that into a simple symbolic representation of the behavior of gas. So this is the behavior of a gas right here in the most concise way. You can't get more concise than this, that's the complete description of the behavior of an ideal gas. And so this is what we call empirical. Do you know what empirical means? You hear this term used a lot, in science. Empirical data, or empirical this, empirical that. Empirical means based on observation. So this is a law based on observations. So let's say we have the ideal gas law like this. Okay, is this where we stop? Well, sometimes this is all we need. This is where we stop. Other times we start to think about this. For example, why does the volume expand as the temperature goes up? What's the reason for that expansion? And so here is where the hypothesis comes. We're trying to understand this law at a more fundamental level. And the way a hypothesis is defined is this. A hypothesis is a fundamental description of the observations, or the laws, or the patterns and trends. So it's a fundamental description of the law, the patterns, trends, the observations. I'll just say observation. And so here we have this equation that describes, how the gas is going to behave. Why is the gas behaving that way? And so this is more of the why, or what's happening. And so here, one of the hypotheses might be, as the temperature increases, the gas is made up of what? Gases are made up of, well, mostly empty space, but also molecules, right? And as the temperature increases, what happens to the molecules? They go faster. And as they go faster, they're going to have more violent collisions and causing the volume to expand. If the volume can't expand, then the pressure is going to go up, right? And so that would be a hypothesis. And the hypothesis would be just the fundamental description, let's say the ideal gas law. Eventually, hypotheses evolved into theory. And so what's the difference between a hypothesis and a theory? These two terms are often confused. A lot of people think of theory as like speculation. I have a theory of who murdered that, in the crime novel or whatever. I have a theory about this. But in science, a theory isn't like speculative in nature. In science, the theory is an end goal. If we know the theory, then I could predict everything on that table. If I understood the theory would allow me to figure out that entire table without having to observe it or measure it, which would be quite great. Versus that table's from empirical data. That table's from empirical data means that table comes from what? In other words, there are two ways I can generate a table like that. One way is I can generate it empirically. And so that table is in fact from empirical data, meaning that table comes from observation. There's another way I can generate a table like that, and I can generate it theoretically. The same thing goes with laws. You can have empirical laws, and you can have laws based on theory. In fact, the ideal gas law was originally determined empirically. It wasn't until later, using kinetic molecular theory. You remember kinetic molecular theory of gases? What comes to mind when you think of kinetic molecular theory of gases? You think, okay, kinetic means what? Motion. Molecular means Molecules in motion, right? Kinetic molecular theory. And so from kinetic molecular theory, we can also derive the ideal gas law. So there are two ways that the ideal gas law was derived. One was empirically, based on all those old experiments from the 1700s, 1800s. And then two, theoretically, which came much later, at a much later time, people using kinetic molecular theory and the equations involved in kinetic molecular theory were able to determine the ideal gas law mathematically and based on physics. Okay. But the theory should be what, normally when somebody comes up with a hypothesis, it's tentative, And so this fundamental description of observations, etc., this is tentative. So there were some observations back in Chem 1A. One of the observations was the conservation of mass. That is, if you do a chemical reaction, the mass before the reaction is equal to the mass after the reaction. And so there was no change in mass, total mass. Right? Do you guys remember that one? Lavoisier. And so that conservation of mass led to this pattern. This pattern was a consistent pattern. Whatever reaction they tried, they always saw the same thing. Mass was conserved. And so they created a law. It's called the law of conservation of mass. That is, there's no change in mass, basically. Do you know what the hypothesis for that was? Some of the early hypotheses, like Dalton, I think Dalton came up with the first. Probably there are people that preceded Dalton, but what was Dalton famous for? Dalton. He was pretty much famous for a theory. Do you recall what theory Dalton was famous for? No? Okay, the theory that Dalton was famous for is Dalton's atomic theory. And so what happened was, because of the conservation of mass, what Dalton proposed was that matter consists of atoms. There's a fundamental limit to how small a piece of matter can get, and that fundamental limit is called the atom. Versus there are other people who are hypothesizing that matter was infinitely divisible. That is, you can get smaller and smaller pieces of matter, and this goes on infinitely long. So you'd have an infinitesimally small piece of matter, but that's not the case. And there are certain observations. One of the observations was this. There are other observations that led to that, I think. But that was the hypothesis. Now, if you think about the hypothesis, so somebody comes along and hypothesizes. This is back in Dalton's times. Dalton was right, like early 1800s, late 1700s, right? So Dalton proposes that atoms exist. And this is why we see these observations. And so he hypothesized this, but there are a lot of people who are skeptical of this. A lot of people who didn't believe in atoms. And so what proof did Dalton have? Or actually, what proof do you have that atoms exist? If somebody came up to you and asked you, prove it to me. I'm not going to believe you until you prove it to me or you show me some evidence that atoms do indeed exist. Because I've never seen an atom. And so how do I know, you aren't making this up? How do I know that this is not some scientific hoax or scientific misinformation or disinformation? How do you know? Think about that. Could atoms have been misinformation or disinformation all this time? Well, if a group of scientists said, man, that Dalton guy, he's just spewing out lots of misinformation and disinformation. Pay no attention to that guy. In fact, we should probably silence that guy because what he's saying is crazy. I can take a piece of copper and divide it into smaller and smaller pieces. And I can get a piece so small I can't even see it. So that Dalton guy's out of his mind. He's crazy. He should be ostracized from the scientific community. The scientific community being the community that believes, I believe that matter is infinitely divisible. So, what proof did Dalton have? That constant mass is conserved? Mass is conserved? Do you believe that? Oh, I'm going to need some bigger proof than that, right? I'm going to need some heavy-duty proof. Well, anyway, it turns out that the beauty of the scientific method is nobody should be silenced. Nobody should be censored. Everybody should have the opportunity to make a point. And it's your job, if you don't agree with somebody's hypothesis, it's your job to tear it apart. You can tear it apart. That happens all the time. You're missing this. You don't understand that. That's this type of thing. And then you can make convincing arguments to either support or not support such hypotheses. But I think back, in Dalton's time, this was a very tough question. I mean, why do you believe in atoms? Well, the first time I heard about atoms was like in 7th grade, I think. In 7th grade, in science, I learned about atoms. And so if I told you that I have proof, my 7th grade science teacher told me about atoms, that's all the proof you need, right? If your 7th grade science teacher tells you that atoms exist, then you better believe them, otherwise. But obviously that's not enough. And so when I think about this, and Dalton, obviously there were lots of people skeptical about atoms. And Dalton had to defend. What did he do? How did he prove that atoms exist? How he proved it was he connected certain observations. He said, if matter were infinitely divisible, you could get smaller and smaller amounts. Would H2O always be 2 parts hydrogen? If you think about H2O, could you have, if matter were infinitely divisible, could you have H2.10 or H2.20? In different, or maybe H2, almost 2, let's say 2.000 or 1.999. And so there are certain arguments that Dalton can make based on observations, based on facts, that eventually he could convince enough people that atomic theory makes sense, right? And so the atomic theory part here, this isn't accepted. Now, accepted is getting tricky because you hear talk, the scientific consensus, the scientific consensus says this, right? The scientific consensus says that global warming is a huge problem, correct? And you hear this in all the time. I hear about the scientific consensus. But when I think about scientific consensus, science is not always consensus. When I started off in science, I thought, man, science, there are a lot of mean people in science. Well, they aren't necessarily mean. You give a talk or something and you have lots of critics. Everybody's a critic. You write a paper and you submit it for peer review, and you get lots of negative comment. Why didn't you do this? Why didn't you do that? All these negative comments. But, when you think about it, that's what makes the scientific method so great. And that's why it's withstood, this long period of, I guess, scientific prosperity. We have this long period of scientific prosperity because the scientific method was allowed to work. And is there a scientific policeman? Is there somebody assigned as a scientific policeman? No, there's nobody assigned as a scientific policeman because that's not how science works. How science works is it undergoes peer review. That is, people pick apart things to see if the arguments for it are sound. And so anyways, accepted means just generally accepted. And this would be fundamental rather than a tentative fundamental. And so once we hit theory, then it means something special. It's not speculative in nature. the theory is very sound, and this is what we're ultimately after. We don't always get there. You know, sometimes we just stop at patterns and trends and just leave it at that, because even patterns and trends is very useful. Or sometimes we don't even see that, we just see observations, so we just go based on, you know, factual observations here and there. But, you know, we work in all parts, but ultimately we would like a theory, because what theories allow us to do is it allows us to understand the things at a more fundamental level. And if you understand things at a more fundamental level, then what you can do is you can make predictions. And so a theory should be able to do two things. One, it should offer a fundamental description of the underlying observations, laws, whatever. And two, it should be able to predict new, unforeseen observations, laws, whatever. And so, you know, from the law of conservation of mass, we end up with Dalton's atomic theory, and Dalton's atomic theory predicted the law of multiple proportions. Or let's see some other examples. Other examples would be this, the periodic table. If you look at the periodic table, and memory's always been an issue for me, and so I was taking this memory class to try to improve my memory, and it was given by a world record. It was just online, recorded. It was given by a world record holder in memory, and one of the first things he did was he memorized the periodic table, so that, you know, if anybody asked him what the symbol of the element is, he could spout it out, or the number, or if you gave him the number, like element number 99, you know, what is that? He could tell you. But, you know, that wasn't very impressive, and that wasn't very impressive because he didn't say whether he memorized the pattern or not. You know, sometimes if you look at element number 99, or element number 75, can you tell me anything about that element? Its properties or anything? And so we have all these observations, and then we organize it into a pattern. This is a pattern. And these patterns are based on chemical and physical properties. And then, okay. There's not necessarily a law associated with it, but there is a consistent pattern there. The law might be, you know, just this law of the periods. The law of the periods would be that the properties transition smoothly from metallic to non-metallic. The law of the families would be, you know, elements in the same family have similar chemical properties and similar physical properties, and that varies. But then we come to the hypothesis. Now, the periodic table came before the theory. You know, was that periodic table derived empirically or theoretically? Actually, you know, when you think back at Mendeleev, it was derived empirically, just from observations, because he didn't know something. You know how this is grouped. What's a hypothesis? Now we have this pattern. Can you come to a hypothesis? It's still pretty tough, isn't it? It's a hypothesis. And so we look at that, but it didn't come out until much later. And so in this sense, the underlying description of this periodic table did come about theoretically. The periodic table itself was derived experimentally. And that theoretically came from something else. And that something else was this. You know, what's the sun made out of? Hydrogen. And the sun is like a giant light bulb in the sky, right? You get lots of white light from that. And so some scientists tried to make a hydrogen lamp on Earth. If you have a hydrogen lamp on Earth, you know, you try to mimic the sun, and you should be able to get white light. Right? But did the hydrogen lamps on Earth make white light? No, why not? Because the sun's made out of hydrogen. The hydrogen lamp is made out of hydrogen. Why aren't we getting white light from the hydrogen lamp? And so that was unusual because they were expecting white light from a hydrogen lamp, actually, but they didn't get the white light. And so that was an observation of an unusual light pattern in the hydrogen lamp. It should have given us white light. It didn't. Was there a pattern? There was a pattern. And then from that pattern came a law. Do you know what the law is on the hydrogen lamp? You may or may not remember this one, or it's called the Rydberg law, or the Rydberg law. Does that sound familiar? The Rydberg law? So we got the Rydberg law, and then there was a hypothesis. You know, the hypothesis was that these lines that we see in the hydrogen spectrum come from electrons bumping from one orbit to another orbit. Do you remember that hypothesis? Who did that hypothesis come from? That hypothesis came from Bohr, B-O-H-R. Does that sound familiar? And that was called the Bohr theory. And the Bohr theory said that the electrons in an atom orbit around the nucleus, and that when light is given off, these electrons transition from one orbit to another orbit, or when light is absorbed, they transition from one orbit. We have emission and absorption. And then that led to the Bohr theory. The Bohr theory, there was one major problem with the Bohr theory, and the one major problem with the Bohr theory is that it could not make any predictions. The Bohr theory could not predict helium, you know, the next element on the periodic table. It failed. And so if the Bohr theory could not predict helium, but it was good at explaining hydrogen, what happened to that theory? The Bohr theory was abandoned. So we no longer think of electrons in orbits. In fact, electrons in orbits is entirely wrong. Electrons in what now? When we think about electrons in atoms, we think about electrons in, not orbits, but we think of electrons in orbitals. And that's correct. You know, and so from the Bohr theory, which was abandoned because it could not predict helium or anything more complicated than that, we got a new theory. So Bohr theory was dropped, the new theory replaced it. What was the name of the new theory that replaced it? The Bohr theory. Okay. Quantum theory, exactly. Quantum mechanics, quantum theory. So quantum mechanics, quantum theory predicted it. Now, the periodic table was derived empirically, but it was later determined that the periodic table and quantum mechanics, the quantum theory, go hand in hand. Do you see why? Because the organization of the periodic table can be explained in both empirical terms, that is, the chemical properties, the physical properties, and it can be explained in theoretical terms. And in theoretical terms, we divide the periodic table into different segments, like this middle block. What do we call this middle block here? There are different names for this middle block of elements. One name is metals, another name is the blank block. The D block. Have you heard that term, the D block? The D block refers to what? D refers to d orbitals, right? And we're filling d orbitals in the d block. That's what. This is the s block, this is the p block, and this is the f block. And so this was derived empirically, the organization, but later verified theoretically because that's what we would predict from quantum mechanics. Yeah. And so the scientific method has led to this long period of scientific prosperity, but it's getting all mixed up because I think politics and science are getting intertwined, and politics should stay out of science. Absolutely. Because politics aren't held to the same, or to the same standards, as far as information verification. Once I was listening to a radio program, and one of the city council members mentioned that, there's studies that show this. It was very interesting. I thought, oh, okay, the study shows this. I'm very interested in the study, but they didn't say where the study was from. And so I called the office because I just wanted the reference so I could look up the study and see it for myself. But he said, oh, sorry, there's no such study that exists, But that wouldn't happen in science. In science, well, and then it was that was what was said on the radio. But so in science, no, people would be digging. They want to not only see the study, they want to reproduce the study. So a while back ago, there have been some famous cases of the scientific method in action. One was, did you hear about the alien life on Earth? Did you ever hear about that? Some NASA astrobiologists were looking at Mono Lake in California. Have you ever been to Mono Lake? It's just east of Yosemite. Mono Lake has high arsenic concentrations in the water. And basically there's nothing living in there except little brine shrimp and bacteria. And so these NASA astrobiologists are thinking, how can these bacteria survive in such a high arsenic environment? Because, arsenic and phosphorus are in the same family. And most bacteria are phosphorus-based, like ATP is what? The energy molecule, right? Mitochondria needs ATP, whatever. And so what these NASA astrobiologists hypothesized was that these bacteria living in this lake must be arsenic-based life forms and phosphorus-based. And so in that sense, they're alien because they aren't like normal life. Normal life is triphosphate. And so they predicted instead of triphosphate, maybe these bacteria have triarsenate instead of triphosphate. So, and then they're thinking, well, on other planets, the elemental mix on the planet might be different. I saw a lot of people put the elemental mix of nitric acid, hydrogen, nitrogen, oxygen, but maybe the elemental mix is different on these other planets, and therefore the life might be different in that sense. And so they did some measurements. They took some measurements, and they saw high concentrations of arsenic in the bacteria. And then they published this paper. And so let me show you the paper. And it passed peer review. So that was Mono Lake. So this is a picture of Mono Lake. These are tufa towers, Mono Lake. And then Yosemite's out that way, there. Newfound bacteria thrives in the arsenic-rich waters of Mono Lake. NASA life discovery, new bacteria makes DNA with arsenic. It turns out that, of course, there are skeptics of this, right? And those skeptics, rather than just criticizing, they tried to repeat the experiments. That is, they collected the bacteria and then tried to determine, is the arsenic coming from the DNA or ATP or whatever, the energy molecules, or is it coming from somewhere else? And so this was published in Nature magazine, which is, I think, a premier, I'm pretty sure it was in Nature or Science. It's either in Science or Nature. But eventually what happened was, it was debunked. And so it turns out that it was due to a suspected contamination issue. And this is how science polices itself, you know, just in the normal way. Nobody went out and said, you guys are crazy, you know. They didn't say that. They just said, okay, what does the data show? That's what it should. Or, you know, pushing anything. Anyway, I have this here. This was developed in 2012. This is very exciting. I remember when the first story came out, I thought it was really pretty exciting research. You know, I thought that would be really cool. Anyway. All right, I have runny nose, but it's allergies. Not my second case of Omicron. Okay, so I saw that a lot of people wrote down the name of this. That's good. You guys remember the name for this? What is that? Nitric acid. Are you guys still pretty good with nomenclature? Okay, look on the middle chart there. HClO4. What's the name of that? The acid at the top of the chart. Hydrochloric acid is number 4. What's number 1? Perchloric acid is correct. That's perchloric acid. Now, let me talk about patterns and trends, observations. And I used to study, when I studied chemistry, more of an observation type, you know, just memorize things. And so when I was learning nomenclature, I would get flashcards. But I found flashcards pretty difficult. Because when the exam came up, I had a hard time remembering the numbers and the charges and that kind of stuff. And so what I found much more effective was writing it down. So if I was doing perchloric acid or something like that, or perchlorate, I'd write it down. I'd write it down over and over, maybe about 500 times for the ones that are hard. You know, less than that for the ones that were easier. And eventually, I got it into my motor memory. So it was like riding a bicycle. Somebody said perchloric acid, boom, I'd have it down. It's just motor. But, you know, that's not very effective, I found, because there's too much stuff to memorize. Right? There's just too much. And so rather than memorizing, like, things, instead, you know, like that chart, somebody asked me, and you might think this is ridiculous, or you might think this is a student who was really trying to do well. They asked me, should I memorize the chart? That's like the periodic table. Should I memorize the periodic table? No, there's no reason to memorize, at least not like the memory guy did. You know, what would be better is to memorize the pattern in the periodic table. When you get like a PhD chemist, you know, I had to memorize the first 4 rows of the periodic table, and then a few other elements. And that was enough. I had to memorize that. No reason to. And definitely no reason to memorize just the number and the elements of this. You know, you want to know the pattern, the period, areas, those kind of things. And the same thing with this. When you ask me, should I memorize this? What does that mean? If I say you don't memorize this, then you know what you do? You look at it, and then that's too much jumbled information, forget it, and read it back. That's what most people do. They see a table like this, or a table like this, and they go, wow, forget it. I'll just look it up. If I need something like this, I'm going to just look it up. But no, you should take it up to the next level. That would be observation. You know, what we should do is we should look for patterns there in that. And so I showed you one pattern, you know, HBr, HCl, HNO3, right? But we should be looking for other patterns as well, because that's going to be proved to be much more useful than organization. So one of the patterns in nomenclature, and let me just review this because in case you might have forgotten some of these, and they're easy to forget if you don't use them all the time. But let's start off. So I know this, the second period easily. Boron, carbon, nitrogen, oxygen, fluorine. So, these are useful to know. But let's take a look at the ides. Like, for example, what is boride? Boride ion. Have you ever heard of boride ion? Yeah, what would the charge be? Boride. What would the charge be on boride? -1? Okay, that's a good guess. Ide, negative. That's good. So you associated ide with the negative ion? That's good. But, you know, as far as patterns go, I would do something like this. What is fluoride? Fluoride is what charge? Actually negative, like chloride. Now chlorine, actually let me write this down a little bit lower. Chlorine would be Cl minus, that would be chloride. What's oxide? Oxide? -2. Nitride? -3. Carbide? -4, which means boride should be, according to this pattern, boride should be -5. But -5 is too much, you know, for little boron to hold on to that many, because boron only has 5 protons. If you give it 5 more electrons, it's 10 electrons with 5 protons is too hard to hold on to. This is going to be an unstable ion. So boride, we don't. Carbide, though, carbide does exist, right? Silicon carbide, so carbides do exist. So boride's probably at the limit, but that's what we would predict based on the pattern. So it's much more useful to know the pattern than just to memorize, right, the ions themselves. So let's look at the 8s. Now, borate does exist. Can you tell me what borate, the formula for borate, what it should be? Borate is actually used to be mined in California. I don't know how much. You know, when I was young, little, you know, they used to have borax soap dispensers. Well, borax has regained popularity because of what is that, slime or something. But these borax soap dispensers, they're filled with borax soap, which is powdered. And then there's a little metal lever. You push up the metal lever and some powdered soap would fall, and then you wash your hands with powdered soap. I remember that pretty well. And originally I started off as a geology major, so I went to all the dry lake beds, and one of them they mined borates. So, and then boric acid. Have you heard of boric acid in eye drops and stuff? Yeah. So boric acid is still used. What is the formula for boric acid? You know? HBr, hydrobromic acid. And so, in fact, there's a town named after boron, you know, called Boron, California. That's where they discovered boron. Anyway, let me make this quick. I have lots of stories about boron, but we'll move on. Boron is in group 3A, or group 13. You know, there are different numbering systems. You know, we have the 3A, 3B. Do you know what family 3B is? Scandium, yttrium, lanthanum, actinium. That's group number 3. That's 3B. And so we have 3A, 3B. And the way I memorize this. So you should memorize borate too, but it's easy to memorize. It's in group 3. It has 3 oxygens and it has a charge of 3 minus. So that's one way. There's another way you can remember borate, going backwards like we did with boride. What's carbonate? So we memorized this one. Group 3, 3, 3. What's carbonate? CO. Close, but not 4 oxygens. Carbonate is, 3 It's CO3. What's the charge on carbonate? 2 minus. That's good. So borate, carbonate. What's nitrate? NO3 minus. There's no oxidate, so we'll skip that. What is fluorate? What is fluorate? Yeah, that's correct. FO3 and the charge? Well, it's negative, but we've bottomed out. You know, we can't go lower than -1. I mean, or higher, or whatever you want to say. And so once it bottoms out, it stays. So fluoride is FO3 negative. This means what is chlorate? Chlorate is ClO3 negative. So this is a lot. You know, I wouldn't do the flashcards. I wouldn't do the writing for perchlorate because perchlorate is easy. It just takes a little bit of time. The time it takes is start at borate, and then all these have 3 oxygens, and then go to chlorate. Chlorate's 3 oxygens with a -1, right? And then what does per mean? Per means 1 more oxygen, same charge. So perchlorate is easy. If I know what chlorate is, then I can figure out what perchlorate is. Perchlorate would be ClO4 minus. And then perchloric acid is just add the H plus. So perchloric acid is HClO4. What is boric acid? Boric acid is H3BO3. Carbonic acid, H2CO3. Nitric acid, HNO3. We have, what's this? Fluoric acid, HFO3. Chloric acid would be HClO3. Perchloric acid would be HCl4. And then with the ides, we have acids as well. So for example, hydrofluoric acid would be HF. You know, we have the hydro. Okay. So there are different ways we can name these things. So for example, water as an acid, how many hydrogens would be required? Well, hydronium we're thinking, but water itself would be H2O. And so H2O could be called hydroxyic acid, you know, like this, hydroiodic acid or hydrofluoric acid, etc., hydrochloric acid. They follow the same pattern. There are different ways we could name water, though. Okay, then we have the ites. If I know the ites, then the ites are easy. I don't have to memorize any of the ites. So, for example, if chlorate is this, what is chlorite? If chlorate is ClO3, then chlorite would be ClO2, right? And so chlorite is ClO2 charge? Minus. And then what would hypochlorite be? So I'll have the hypo prefix with the ite suffix. Hypochlorite would be ClO minus. And so you don't have to have all these memorized. The only thing you have to know is borate, because if you know borate, then you can figure out the rest based on the pattern. And so this is often what we do in science. We look for these patterns. And did I talk about the TED Talk? Yeah, okay. And so you would just stare at this. Now, we got this pattern here, and then we start to, is there a law? I guess this is the law of the oxygen. The law of the oxygen is the 3 oxygens. And the law of the charges decrease by 1. But then you might think about the hypothesis. What is the hypothesis? Why do we see this pattern? What's the fundamental underlying description of what's going on here with the oxygens and the bonding and everything else? And so that's what we look for next. And there are, we'll talk about these more probably later. There's a little bit of history and some chemistry in these patterns. But for right now, we don't need to know that. We don't need to know the hypothesis. We don't need to know the theory. We just use the pattern. There's one more pattern that I want to share with you here. And one more pattern is for this other loss here. So, for example, rather than having phosphorus-based life or phosphate-based life, we have arsenic-based life or arsenate-based life. What's the formula for arsenate? Well, if you don't know the formula for arsenate, you could derive it based on a pattern. And so what is the pattern? The pattern starts off with silicon here. And so we could have silicide. Silicide would be silicon 4-. But what we're going to do is we're going to go straight to silicate. You know what the formula for silicate is? Probably not, because it's not so common in Chem 1A or Chem 4. But silicate is SiO4 4-. Now, this one is not terribly difficult to memorize because silicate is in group 4A. It being in group 4A, we have 4, 4, 4. That's one way to memorize silicate, 4, 4, 4. Group 4, 4 oxygens, 4- charge. Okay, next to silicon is phosphorus. Phosphorus is underneath nitrogen here. And so phosphate is what? What's the formula for phosphate? PO4, 3-. Next to phosphorus is sulfur. What's the formula for sulfate? SO4, 2-. Underneath sulfur is selenium. What's selenate? The formula for selenate. Now this is where you have to know the pattern. It's SeO4, 2-. So selenate has the same number of oxygens as sulfate and the same charge. It's like fluorate and chlorate. Below phosphorus is arsenic. So below phosphorus is arsenic. What's the formula for arsenate? Arsenate, the formula is ASO4, 3-. You're right, that's it. ASO4, 3-. Below selenium is tellurium. So what is tellurate? Tellurate. TeO4, 2-. Below silicon is germanium. What's germanate? GeO4, 4-. You're right. That's it. So do you see the power of knowing the pattern is much more useful than just straight memorization of these. That goes for chemical reactivity too. So if we're looking at the chemical reactions or properties of nitric acid, what are you going to do? Are you going to list every single chemical compound and element that nitric acid reacts with? Will nitric acid react with hydrogen? Will nitric acid react with helium? Will it react with sodium chloride? Will it react with all these, right? Now, what we're going to do is we're going to look for patterns here. And you probably have already categorized chemical properties into different types. So what are some of the types of chemical properties? Like acid-base reactions, right? Acid-base properties. What else? What else would be like combination, decomposition, precipitation, neutralization, effervescence, all these different ones, right? But that's too much. That's still too individualized. What I'd like to do is I'd like to subcategorize chemical properties into 3 types. So 3 types of chemical reactions. three basic types of chemical reactions. And what are the three basic types of chemical reactions?
The first one is acid-base. And with acid-base, there are three subtypes of acid-base reactions. Since I'm running out of time, I'm just going to list them here. Arrhenius, Bronsted, and Lewis. Okay, then we have redox, which is another major category. In redox, we have things like combustion. We have combustion, single replacement, etc. There are more subcategories there. And the third category is metathesis. In metathesis, we have things like double replacement, etc.
So when I ask a question like, what are the chemical properties of nitric acid? This is what I'm asking. What are nitric acid's acid-base properties? What is nitric acid's redox properties? And what is nitric acid's metathesis properties? If I can list those, then I pretty much have all the chemical properties of nitric acid, at least the major ones. You know, these are the three main types or categories of nitric acid. This last one's metathesis. I'm going to go over this again. So metathesis, metathesis. What time do we go till? 12:55? Okay, it's already 12:55. So we'll continue this. Tomorrow we're meeting in the lab room, which is Chem 162. So see you there.